A single stray speck of dust, invisible to human eyes, lands on a freshly printed circuit board. Deep inside a modern electronics factory, high-speed machines place thousands of tiny metal parts onto thin glass plates every minute. If just one copper trace is bridged or a solder connection sits off by a fraction of a millimeter, an entire smartphone or car control computer becomes useless scrap. For decades, factory quality control relied entirely on human workers sitting under bright magnifying lamps. Human eyes scan thousands of identical boards every day, searching for microscopic cracks and misplaced parts. As circuit components shrank down to the size of a single grain of pepper, the human eye hit a firm natural wall. Fatigue set in, mistakes slipped through, and entire shipments of electronics failed after reaching store shelves. To solve this massive manufacturing bottleneck, engineers built automated optical inspection systems directly into the heart of the assembly line. Known as AOI, these machines act as silent, unblinking guardians, positioned right after components are placed on a printed circuit board. Rather than relying on simple overhead lights, an AOI system floods the green board with bright, colored light coming from multiple angles at the exact same instant. Red, green, and blue light-emitting diodes shine across the metal pins and solder paste from sharp low angles and direct top angles. Because smooth metal surfaces reflect light like clean mirrors, the angle of reflection tells the machine the exact shape of every single solder joint. A flat surface reflects blue light straight up, while a curved or lifted lead reflects red light off to the side. At the top of the dark inspection chamber sits an ultra-high resolution CMOS camera sensor. These specialized CMOS sensors capture hundreds of images per second with extreme precision, recording every square micron of the board in sharp focus. The camera converts photons into digital bits, transforming a complex physical board into billions of data points in a small fraction of a single second. Once the camera image is captured, the internal computer runs a rapid algorithm known as a golden image comparison. The factory feeds the system a digital master file, which represents a mathematically perfect circuit board with zero flaws. Every pixel of the freshly made board is laid directly over the golden image to spot any subtle difference in color, shape, size, or light intensity. If a tiny resistor has rotated by just 3 degrees, the algorithm flags the mathematical mismatch instantly. The comparison takes less than 50 milliseconds, allowing the system to inspect every single board, moving down fast PCB assembly lines without stopping production. When a defect is found, the automated unit immediately alerts the assembly computer to halt the placer machine before it ruins hundreds of additional boards. Without this rapid optical check, modern technology supply chains would completely collapse under the weight of expensive product recalls. A modern smartphone motherboard contains over 2,000 microscopic surface mount components packed into a space no bigger than a stick of gum. Finding a cracked solder joint after a device is fully glued shut costs hundreds of times more than catching it on the open circuit board. The demand for extreme optical accuracy gets even tighter when moving from circuit boards into semiconductor packaging. Inside a clean room, microscopic silicon chips are stacked on top of one another and connected with wire threads much thinner than a single strand of human hair. Here, optical machines must spot micro-defects that are measured in tiny fractions of a single micron. At this microscopic scale, light behaves in tricky ways, requiring specialized lasers and structured light patterns. Standard white light bleeds around microscopic edges, so short wavelength blue lasers shoot fine grid lines across the chip surface. By measuring how the grid line bends as it glides over microscopic bumps, the optical system calculates height differences down to the thickness of just a few atoms. This leap in optical technology completely changed the role of the human worker in global electronics plants. Operators no longer spend long 12-hour shifts staring through dark microscopes until their eyes burn with strain. Instead, skilled technicians monitor digital consoles that collect real-time data from dozens of automated optical inspection machines running in parallel across the vast factory floor. In the early days of machine vision, small changes in room light or factory dust caused constant false alarms. A slight shift in room temperature could expand a metal frame and throw off the camera position by a few microns, bringing the entire assembly line to a sudden halt. Engineers spent years writing adaptive software that could tell the difference between harmless dust and a true physical break. Modern inspection systems now layer advanced machine learning software over standard pixel comparisons. The system learns to recognize normal variations in solder shine, allowing it to ignore harmless surface marks while hunting down true structural micro-defects. This intelligent filtering cuts down false reject rates, keeping high-speed production lines running smoothly while maintaining absolute quality control across millions of printed circuit boards. The true stakes of these microscopic checks reach far beyond consumer handheld devices into critical life-or-death hardware. In electric vehicles, high-voltage power boards route massive amounts of energy to brake controls and steering motors. A single hidden hairline crack in a solder joint can cause an entire car system to fail without warning while traveling down a high-speed highway. Automotive manufacturers now enforce absolute zero-defect rules before any electronic circuit board is installed into a motor vehicle. Automated optical inspection units log a complete digital record of every single solder joint scanned, saving microscopic photo proof for every board built. If a safety issue ever arises years later, engineers can trace the board back to its exact second of assembly and optical scan. To catch micro-defects hidden behind tall surface parts, advanced AOI systems now use three-dimensional optical imaging heads. Multiple CMOS sensors mounted at sharp diagonal angles view the circuit board from 4 directions at once, building a precise height map of every object. This multi-camera approach solves the old problem of dark shadows cast by big capacitors onto nearby tiny chips. Inside the machine enclosure, physical conditions must remain perfectly controlled to protect the delicate optical process. Heavy anti-vibration legs keep the steel machine frame isolated from floor shakes caused by nearby factory equipment. Clean air blows continuously through fine internal filters to ensure floating dust particles never land on sensitive camera lenses or distort the fine image analysis. Every modern computer and electronic device in use today pass through these silent light chambers before reaching consumers. People rarely think about the billions of microscopic checks performed inside fast assembly lines to keep daily devices running smoothly. Yet our complete reliance on modern digital tools rests directly on this invisible layer of precise machine vision and automated optical inspection. In aerospace manufacturing, electronic circuits must endure extreme launch vibrations and freezing outer space temperature swings. Printed circuit boards built for satellites undergo rigorous optical checks at every stage of production, from raw copper track printing to final protective coating layers. Catching a single lifted chip pin early prevents a multi-million-dollar space mission from failing permanently in orbit. Beyond visible light, high-end optical systems use invisible infrared waves to look underneath protective surface coatings. Infrared rays pass through thick, rubbery coatings, revealing hidden solder short circuits and trapped moisture pockets underneath solid layers. By capturing images across multiple light wavelengths, automated inspection tools uncover hidden defects that would remain invisible to standard optical cameras. As microchip design advances into three-dimensional stacked chiplets, the boundary between circuit board assembly and chip fabrication disappears. Optical inspection systems are pushing into advanced sub-micron light physics to examine stacked silicon layers before they are glued together forever. A single undetected flaw at this tiny scale destroys an entire stack of expensive, custom-made microprocessors. Late at night, inside silent automated factories around the world, bright pulses of multicolored light flash rapidly behind heavy steel panels. Millions of circuit boards pass through every day, each scanned, analyzed, and approved by fast digital eyes. The constant search for microscopic defects remains an invisible war fought in milliseconds, protecting the hidden physical backbone of our modern world.